Okay, so this is section 4.4. We're talking about indefinite integrals and the net change theorem. Now, indefinite integrals, frankly, are probably a little bit easier than definite integrals in the fact that an indefinite integral doesn't have bounds. So really, you're just going to end up using antiderivatives. And that's pretty much all there is to it. And then you're going to add a c because we won't have any bounds. The net change theorem is probably the more important piece of this lesson. So we're going to kind of fly through the indefinite integral part because it really is the same thing as we've been doing with definite integrals, just without bounds. And then we'll talk about the net change theorem. So we've got a little bit of a review here. A few problems here just to remind ourselves how to take definite integrals because these all have bounds and some of the things to look for. So in the first one, remember that the fundamental theorem of calculus, part 2, says that we're just going to take the antiderivative, plug in the upper and lower bounds, and then subtract the results. And that's going to give us the result of the definite integral. So the antiderivative of x to the 1/2 would be x to the 3/2 divided by 3/2 is multiplying by 2/3, and we'll evaluate that from 0 to 1. So that means we're going to plug in 1. If you plug in 1, the good thing about 1 is 1 to any power is 1. So 1 to the 3/2 is still 1. So you get 2/3 times 1, which is 2/3. And then if you plug in 0, 0 to any power is 0. So you get 2/3 minus 0, or 2/3. Not very challenging. Second one. The second one is put there because, a lot of people are going to say, okay, well, the antiderivative is x to the -2, and then we'll divide by -2, which is the same as multiplying it by -1/2. You can do all that, and then you can try and plug in your bounds. The problem is, x to the -3, the original function, is the same thing as 1 over x cubed. Well, that is specifically undefined at 0, and these bounds go from -1 to 3, which covers 0. Therefore, this one cannot be done using the fundamental theorem of calculus. Cannot be done using the fundamental theorem of calculus because it's not defined on the interval that's given. And then in number 3, the antiderivative of secant x tangent x is just going to be secant x. And we'll evaluate that from pi/4 to pi/3. So that's going to be, secant of pi/3 minus secant of pi/4. And if you're like me, I don't necessarily always have those values memorized. What I do know is that they are reciprocals of cosine. So I do know what cosine of pi/3 is. Cosine of pi/3 is 1/2. Therefore, the reciprocal is 2. Cosine of pi over 4 is square root of 2 over 2. Also could be written as 1 over the square root of 2. Flipping that over is just going to give you square root of 2. So it's 2 minus the square root of 2. All right, and again, I definitely strongly suggest practicing using some mental math to be able to figure that stuff out. The better you get with that, the better off you're going to be overall. All right, so these above problems were, as I said, these were definite integrals because they had bounds. When there's no limits of integration present, then the problem is an example of an indefinite integral. So remember that a definite integral, as you can see from above, results in a number. We get an actual result. There's some kind of a number left over at the end of these things. Whereas an indefinite integral is a function or a family of functions. So very much like the antiderivative would give you a family of functions if it was the general antiderivative. All right. A lot of these are going to look familiar if you've looked at the flashcards which were provided to you. The first one, it just says that the integral of some constant times f of x dx is the same thing as the constant times the integral of f of x dx. Or in other words, you can pull the constant out to the front of the integral. Okay, and number 2, it just says that if I take the integral of two functions either being added or subtracted, I can split them to be the integral of the first function, dx, plus or minus the integral of the second function, dx. So we can separate integration through addition and subtraction. In the third one, k is a constant also. So if you take the integral of a constant, well, if you think about it, the antiderivative of a constant is always kx, for the constant times x. And because it's indefinite and there's no bounds, we must put plus c. All the rest of these are just your rules. So number 4 is your basic power rule, which says if I'm going to take the integral of x to the n power, where n is some number, then I'm going to add 1 to that exponent, and then we're going to divide by that new exponent. And don't forget plus c. Again, the plus c only occurs because it's indefinite, there's no bounds. It's just like taking an antiderivative. And then all the rest of these are your trig functions, so we'll run through those real quick. The antiderivative of sine is negative cosine of x plus c. Antiderivative of cosine is sine of x plus c. Antiderivative of secant squared of x is tangent of x plus c. Antiderivative of cosecant squared, be careful on this one, is negative cotangent of x plus c, because the derivative of cotangent would give you negative cosecant, so the antiderivative of a positive cosecant squared would give you a negative cotangent x. Antiderivative of secant x tangent x is going to be secant of x plus c. And then again, the antiderivative of, the integral of cosecant x cotangent x dx is the antiderivative of that, which is going to be a negative cosecant x plus c. And again, you just kind of have to think backwards when you're doing the antiderivative or integrals of trig functions, at least for now. All right, so again, these should be relatively quick and easy problems to be able to do. So we're going to run through these very fast. I'm taking an indefinite integral. It's really just like taking an antiderivative. So the antiderivative of x to the fourth is 1/5 x to the 5th plus c. Boom, done. Integral of 6x minus 12x cubed minus 5. Antiderivative of 6x is going to be 3x squared. Antiderivative of negative 12x cubed is going to be negative, let's see, x to the fourth, so dividing by 4 is 3. Negative 3x to the fourth, and then minus 5x. Don't forget the plus c. Antiderivative of 2 cosine of x is 2 sine of x. Antiderivative of secant squared is tangent of x. Don't forget the plus c. And then in the last one, got a little bit of work to do because that's a quotient that we're not really familiar with. So I could change the sine squared to be 1 minus cosine squared. Probably doesn't help me out though, because that's actually adding an addition or subtraction to my denominator. It actually makes it more challenging. What I can do, however, is we can rewrite this as cosine of x over sine of x times 1 over sine of x dx. And why would I do that, you say? Cosine of x over sine of x is cotangent of x. 1 over sine of x is cosecant of x. Now it is in a familiar form. As a matter of fact, it's right above this on the same page. The antiderivative of cotangent of x, cosecant of x, is going to be the negative cosecant of x plus c. Okay, sometimes you have to do a little bit of algebraic work to get it into a position that you're used to. Okay, a little bit of true-false here. So the first one, number 8, says the integral of 5 f of x dx is the same thing as 5 integral f of x, and that is a typo. There should be a dx, otherwise that would definitely have been a false statement. But this is now a true statement with the addition that I just put in there, because it's just pulling the constant out to the front. The second one says, I'm going to take the integral of some function squared dx and say that that's the same thing as the integral of that function dx, the whole thing, squared. Well, these two are two completely different things. It's different to square the function and then take the integral, as opposed to taking an integral and then squaring it, because technically this second piece means the integral of f of x dx times the integral of f of x dx. And that's not the same thing as squaring the original function. So this is false. Okay, and the second one, it says I've got the integral of f of x g of x dx equals the integral of f of x dx times the integral of g of x dx. This is also false, because we do not have a property that says that we can split through multiplication. We can split through addition or subtraction. So that one is also false. And then the last one, 11, says that I'm going to take the derivative of an integral of f of x dx. Now notice this is not exactly the same thing as that fundamental theorem part 1, because there's no bounds here. So there's no x's for me to plug anything into. But if you really think about it, if I were to take the integral of f of x, it's going to give me the antiderivative of f of x. But then I take the derivative with respect to x, it's going to put me right back to where I started from. So this is a true statement. It will just give you the original function back. All right, so there's all of our review, as well as doing some basic indefinite integrals. Now we're going to get to the application of all this stuff. And we are going to be using the calculator. So if you don't have your calculator, you might want to pause the video, get your calculator out and get it ready. It won't be on this page, but we are for the rest of the unit going to actually be able to use the calculator. And I'm going to be showing you some calculator things that you're going to need to know. All right. First of all, if you've already taken physics and you understand some of this, then you're a little bit ahead of things, which is great. If not, we're going to talk about the difference between distance and displacement. It's a very important distinction here. So displacement, as a definition, is how far something is from the starting position. So how far from the starting position. Whereas distance is the actual amount of space traveled. Actual amount of space traveled or covered. So let me give you an example of something where distance and displacement can be different. So most of us are familiar with a track around a high school football field or something like that. But basically your track kind of takes on this kind of a shape. If you were to run along the inside lane of the track, and that's all I've drawn here. So let's say that this is your starting position right here. If you were to run along the inside lane of the track, the actual distance that you run is 400 meters. Okay, if you didn't know that, that's how long it is around one lap around the track. It's 400 meters. That would be your actual distance covered. However, if I were to run the track all the way over here, while I would have run 400 meters, and I stop right there where I started from, my displacement is 0. I'm actually no distance away from where I started. So you can have a displacement, which is the total distance that you are away from where you started, which is different than the actual total distance that you've traveled to get there. Okay, hopefully that makes some kind of sense. So now how can we use this information here to find velocity? I'm sorry, how can we find this information, so distance traveled and displacement, from using velocity? Well, it's actually pretty simple. The total distance that you traveled, so I'll call it the TD, the touchdown, total distance from A to B is going to be the absolute value of a velocity function, the integral of that, with respect to time, or with respect to t, or whatever the variable is. So the total distance is the integral of the absolute value of velocity. So think about that. We are integrating velocity. That means you're going to take an antiderivative of velocity, which gets you back to position. And then when you're got your position function, you're going to evaluate that at the endpoints. So if you really think about it, the way you would find total distance of traveling somewhere is if I know where my ending position was and I know where my starting position was, and I subtract the difference between those, that's the total distance that you traveled. Well, that's exactly what you're going to get here. If you take the antiderivative of velocity, you're going to get position. I'm going to evaluate the position at one endpoint. I'm going to evaluate the position at the other endpoint. I'm going to subtract them, and that will be the total distance that I traveled. The biggest thing is that we have to take the absolute value of velocity because we've got to make sure all of our distances are positive. Whereas the displacement is still the integral from A to B, but it's just the integral of the velocity, because you can have negative velocities. You can have negative positions. So this is going to take into account the fact that we could have gone forward and backward and forward and backward again. It's going to add up all the positive and negatives and just tell us how far we were away from where we started. So that's the difference. The two formulas obviously are extremely similar. Just know that total distance, because distance itself must be a positive value, is an absolute value of velocity when you take the integral. Displacement does not have to be positive, because we could be 5 feet to the left of where we started, which would technically be like a -5. And that's why the displacement does not have to have the absolute value. So let's take a look at a relatively basic, simple example. What we are given here is we are given a graph. It says the particle moves along the x-axis. The figure shows the graph of the particle's velocity over time. So this is the velocity, and this right here would be time. As a matter of fact, I left off a variable. We're going to put a c out there because there should be a c out there. So a and b are the first two times right here, and then you've got c at the end, and then obviously this one is 0. Time 0. All right, so it says, what is the particle's displacement from time t equals 0 to t equals c? Well, displacement takes into account positive and negative. So if we are integrating the velocity, which is what we have here, this is the velocity graph, we are finding the area between the curves. So the area, which it gives us down here, is 4, but because it's below the x-axis, or excuse me, the t-axis in this case, it's considered to be a -4. So I've traveled -4 units from time 0 to time A. Then from time A to time B, all the area is above the x-axis, so that means that we have traveled a positive 10 units. So basically it looks like we went backwards 4 units, then we went forwards 10 units, and then it looks like, and from B to C, we're going to go backwards 26 units. So it looks like what happened was, that's going to be a -26. So our displacement here, if we add all that stuff up, what is that going to be? -20 units, whatever the units are. If you kind of think about this as being actually on a x-axis, your particle, wherever it started, went backwards 4 units, then it went forwards 10 units, and this is horrible because I'm going to run way off my graph. Then it went backwards 26 units and stopped someplace way over there. So from wherever it started right here, this is where it finished. Now I want to know what the total distance that the particle traveled to get there. Well, again, the idea was it went 4 units this way, then it went 10 units that way, then it went 26 units that way. So we're just going to add up all the positive values from that to figure out the actual total distance this thing traveled to get to its final spot. So that's just going to be 4 plus 10 plus 26. So we take into account the absolute values of all these things. And that's going to be 30, 40. So it traveled a total of 40 units to get to negative 20 units away from where we started from. So it says, give the positions of the particle at times A, B, and C. Well, we've kind of already done that. It's probably out of order. We should have done that first. So the position of the particle at time A is 4 units left of where it started. Now, we know that it started at time 0. We just don't know the position of the particle at time 0. So we can't say that it's negative 4 on the number line or something like that. All we can say for position A is that we are 4 units left of the start. Okay, we don't know where the start was. Had we been given that information, we could do it. All right, at B, so now we went back 10 units. So if we do negative 4 units, then positive 10 units, we are now 6 units to the right of the start. And then we already know that we end up at C, negative 20, so we are 20 units left of the start. Okay, and those are important distinctions. Okay, this was quite a lengthy video. But we will come back and we are going to do basically some examples that I have pulled from prior AP tests. So this is really good stuff to see.